right, let's just give everyone a few moments to drop in. Not that they really need the time anyway. Thank you, viewer, whoever you are out there. If this is Ha, come on am. All right, well, let's get this show on the road. Welcome, tech artists from around the world. It's 3 o'clock Eastern Time. Well, Eastern Time in the United States, that is. It's not 3 o'clock, it's noon. It's 12:30. I've got my head up my butt. I can't, well, needless to say, it's time for Tech Art Talk Live. My name is Chris, and I'm going to be your host for today's session. Now, we are going to be talking about a new series here. Well, actually, it's not really a series. It's going to go on for this week and for next week. And we're going to be talking about ray marching. Now, ray marching is a really cool rendering technique. If you haven't found out about it, well, let this be your introduction because it's really cool. Ray marching is kind of like the less intelligent cousin to ray tracing. Now, ray tracing, we covered this in a lecture a few months ago, and it's a pretty cool technique, but ray marching is even, in some ways, even a cooler technique because it's real simple, it's lightweight, it's fast, and it can be done in real time. And we're going to be showing you examples next week of how this can be done real time, and people are actually doing it inside of VR, doing ray marching in VR, and it's really cool. So it's a way of rendering things volumetrically, and so that instead of rendering actual shapes, polygons, vertices, edges, you know, the traditional CGI 3D geometry, you're going to be rendering in abstract shapes. And we're going to talk a little bit about that today. So let's get this show on the road and start talking about ray marching. Yeah, really fun technique. Okay, ray marching, yes. Okay, now I didn't learn ray marching all on my own. In fact, what I did in order to learn this, it was a few years ago, I went to Jamie Wong's website, and here's a link to it on his page. You can go and check out his stuff. If you want a nice, gentle, kind of like uncrash course version in ray marching, this is an excellent place to start. So this is very cool. And it's all about ray marching and signed distance functions. And so this is the schedule that we're going to be following for this week and for next. So this week we're going to be talking about signed distance functions and just overall concept behind ray marching. And then next week we're going to be talking about shading and then transformations and then how to implement all of this into something like a shader tool, HLSL, or something like UE4, which actually can be done totally. It does help if you understand a little bit of HLSL or GLSL for that matter. And I realize that I haven't covered HLSL inside of Tech Art Talk Live, and so that's what I think I'm going to start in. We covered Python over earlier this year, and so I'm going to kind of like digress after we get finished with ray marching here, and I'm going to start teaching kind of giving a crash course in HLSL programming. It's actually pretty easy and it's not too complicated, but it's pretty fundamental. All right, so let's get this thing. So let's get started about dealing with signed distance functions. Now, signed distance functions is what ray marching is all about. Now, some people call them SDFs, and what a signed distance function is really just a mathematical formula. And it's just a mathematical function that returns the shortest distance between a point and a surface. And that's really all it does. And so really what it's going to do is going to return one of three things. It's going to return if this point is outside of the surface, on the surface, or maybe inside of the surface. And that's all it's going to return, is one of those three things. And it's actually a very, very simplistic function, but sign distance functions are what you use in order to define your world when you're doing ray marching. Now consider a basic sphere. A sphere is really pretty simple, and this is the function for a sphere. It's the square root of x squared plus y squared plus z squared, and then you subtract minus 1. Now 1 is assuming that we're dealing with a unit sphere. Now 1 could be whatever the radius you want. And so if we're dealing with 3 potential places, then we're dealing with outside of the sphere. And here in this case, this would return a sign distance function here would return a value greater than 0. And here, this is the function of 0, 3, 0. And this would give something like that. And that would return a distance of 2, which would be positive. If we are inside of the sphere, it would return a value that is negative. So in this case, we have f of 0, 0.5. That would return 0.5. And if we were actually sitting on the surface of the sphere itself, we would go get a distance value of 0. And so we would get f of 1, 0, 0. And yep, that would return just a plain old 0. So what we're talking about is the point going to be on the surface, inside the surface, or outside of the surface? Now here is what the sphere sign distance function actually looks like. I know it's not very impressive, but this is where some of the really genius of ray marching comes in, because guess what? The world is defined of these little baby functions here. Now here, all we have is a sphere SDF, and all we're sending it is a point and a radius. And so what we're doing is returning the length of this point to the middle of the world, and then subtracting a radius from it. And that's going to return either a positive value, a negative value, or it's going to return something that's 0. And so that's all that there is. This is the formula for a sphere. Not too complicated. Now, if you're going to start dealing with things like cubes, then things are a little bit more complicated, and you have to be more of a mathematician in order to understand them. But how you create a cube inside of a volume is kind of you take the assumption that if the change in x is less than 0, and then the change in or the position in x is between -1 and 1, and so therefore if the object is inside of the cube, then it's going to return something negative, or if it's outside of the cube, it's going to be very positive. But it starts with that basic assumption about x in the first place. And so here is the sign distance function for a cube. It's a little bit more complicated, and so what we are doing is we're starting off with a point, and then so we're going to take the absolute value of this point, and we're going to subtract the x, y, and z size of a cube. Here we are assuming this is a unit cube, and so therefore we're just subtracting float 3 from our position, or the absolute value of our position. And then all we're going to take is the inside distance and then the outside distance, and then we're going to add those two together, and the result of that is going to be the end up results of our sign distance function for a cube. All right. I wish I could say I invented this stuff, but one of the primary innovators is this fellow named Inigo Quilez, and he is a mathematician, programmer, CGI artist over in the Spain, the Basque area of Spain. And this guy is a total genius. If you have an opportunity, go check out Inigo's website. That's iquilezles.org. And go check it out, because it is filled with not only stuff about ray marching, but if anything you want to know anything about computer graphics programming and overall the mathematics behind visualization, this is the place to go, because Inigo here is a freaking genius. If you were to go check out his website, this is what it returned. This is the link that I have. And so I understand that SDFs may not be in everyone's bag of tools of understanding, but something like Inigo's website is definitely a place to go. And so what does he have? He has sign distance functions for all of these shapes. He's got cubes, he's got boxes, he's got rounded boxes, he's got box frames, he's got toruses, he's got tubes, he's got links, he's got cylinders, he's got cones. You name it, He's got it. And so they've got all of these objects in here that show, how to create sine distance functions with all these basic primitive shapes. And he just goes on, and he's got just about almost a shape for everything. But even as it might be, you still don't have enough shapes in order to do absolutely everything. So what do you got to do? Well, you got to drive things up into CSG. Now, we're going to get back to that in a little bit later today, but let's digress and go back to the concept of ray marching. So we know that the sine distance function returns a positive value, a negative value, or 0. Great. All right, so how does that work with ray marching? Well, ray marching behaves a lot like ray tracing, it says, but it's got fewer operations, and you don't have to deal with geometry. You just deal with these sine distance functions. Now, I know that we covered ray tracing back a few months ago, but if you want a real quick ray tracing crash course, go check out this link here that I've got on Scratch a Pixel, and it kind of gives another slower crash course on ray tracing. Okay, so the difference between ray marching and ray tracing is that in ray marching, the entire scene is made out of these SDFs. And then, like ray tracing, you start off with a camera and then your world. And so here I've got my camera, and this kind of like simplistic rectangular structure is my entire scene made up of an SDF. And so the camera, just like ray tracing, puts out these rays, and it sends out these rays, and the rays keep pushing forward in small increments, keeps pushing forward until one of two things. While it is still positive, meaning that it's outside of the surface, it's going to keep pushing forward. And then one of two things is going to happen once it finishes that. It either hits the surface and it returns a 0, or it goes inside of the surface and then returns a -1. So needless to say, when it hits 0 or -1, it just stops and says, okay, here we are. This ray has now hit it, and we now know the distance between the camera and this scene object. Okay, but pushing the ray outside of the camera little bit by little bit is a very ineffective process. And so what these mathematician brainiac guys did, they do something a little bit more complicated. They do something, oh, there we go, this is the same thing. They do something called sphere tracing. Now, sphere tracing is a little bit like what we were doing before, but first, it just uses the SDF to find out, okay, how far is this shape to the camera? Now, we don't really care about the ray so much. Right now, I'm not going to worry about the ray. I just want to find the distance. And then that distance turns back to the camera and says, okay, we can progress this far without intersecting the surface. So then we said, okay, good. We're going to wrap a sphere around the point that we're at. In this case, it's the camera. And then we're going to say, okay, we're going to move along our vector, or we're going to move along our trajectory by that amount. So we move forward that amount. And then from that point, that new point that we have here, we're going to check with the SDF again and find out, okay, how far are we now from the sine distance function? And there it is. It's going and it says, oh, okay, I picked it up here, and I'm going to push forward that amount. So we create a new sphere, and then we push forward that brand new amount. And then the process just continues until something happens. And in this case, it's going to just keep moving. And then finally, when it gets to here, it's going to look for the shortest distance, and it finds the shortest distance, not where the other places were, but it's going to find the shortest distance on the other side of the SDF, and it's going to go, ooh, look at that, I can move here, we're getting close, and then it moves till very close until it hits, or it's just right on the edge there. And so that's what sphere tracing is. And so sphere tracing really helps speed up the overall process of the ray marching and gets it done really, really, really quick. And so this is one of the reasons why ray marching can be done in real time. It's because it's doing just a scarce number of calculations. Okay, here is the HLSL for sphere tracing. And we're going to start off sending in here the camera position. We're going to go in the overall marching direction, which is the vector that we're going to follow. We're going to have a starting point and an ending point. And we're going to say, okay, the start here now equals the depth, and so that basically means that it equals 0. And then what it's going to do is it's going to march along this ray until one of two things happen. And we have a max number of limits that prevent any kind of ray from actually kind of like just shooting off into reality, because if the ray is going is actually going away from our signed distance field, then actually the further the ray gets away from our SDF, then the faster it goes, and so it just keeps on accelerating so that we have the maximum number of steps that we can take. And then so what the first step is, we just take the distance and we say, okay, signed distance function, how far are we away from the camera? And then we check out, okay, if this distance is smaller than some kind of very small number, and we're going to call it epsilon, then we're just going to return out of the function and return the depth that we're at. Otherwise, we're going to implement the depth with the current distance that we've added here, and then we're just going to keep going. Now this does check to make sure that if the depth is greater than or equal to the end point, and if it is, then we're just going to return the end again. But otherwise, we're just going to kick out of the loop until probably we get to epsilon or we run out of actual marching steps, and then we're going to return the distance value. Nice and simple. Okay, that is the heart of ray marching, that function right there. And that's really all that there is. Okay, so we mentioned this before. We said, like, how do you define the world using nothing but these signed distance functions? Well, you create the world using something that's called constructive solid geometry, and that's otherwise known as CSGs. And so what you're doing is you're combining basic elements using very primitive basic operations in order to combine elements together. Now, what do I mean by combining elements? Well, they're simple Boolean operations. And luckily for us, there's only 3 real primitive operations that you can do. The first of that is union. And so you've got 2 objects. In this case, I've got a cube and a sphere. And if you union them, and it combines them together. This is equivalent to the Boolean operation of OR. It's either the sphere or the cube. And so really it gives you a combination. And so this gives us also an AND operation. So it's this and that. Now complementary to that is intersection. And that corresponds to the Boolean operation of AND. So it's got to be inside of the sphere and of the tube there. And so that's why it is an intersection of both this whatever volume is inside of the sphere and inside of the tube, that's going to be the union. And this corresponds to the intersection or the Boolean value of AND. So we've got Boolean OR, Boolean AND, union, intersection. And the last operation that we're dealing with is difference. And difference is kind of like subtraction, because union is definitely addition, so difference is subtraction. But you really can't just subtract one object from another. What you got to do first is you got to say A, and you're going to do the intersection of that which is not B. And that gets a little bit hard on the brain to understand, but remember, we're dealing with abstract volumes. And so this works really well because we don't have to deal with reality. We're just dealing with a mathematical function of reality. And so we're going to go say, okay, give us the intersection of A and not B. And that is the difference. And so as you can see here, it looks like the cone has been taken as a chunk right out of the cylinder here, and that's the difference. And so we have union, intersection, and difference, and that's really all that there is. Translate this into HLSL, we'd end up with 3 very, very small little functions. Check this out. intersection is just the maximum value of A and B. And that's going to return the basic intersection. And that basically is equivalent to your AND operation. And so it's the max of both of these. Union, which is kind of like the addition of it, is really just the minimum. Give us the minimum of the distance A and distance B, and that's going to be the SDF for union. Okay, now difference is a little more complicated, so what we're going to do is go back and give the intersection of A and not B. And so what that is that returns the difference value. And so here are our three functions that when we combine them together, we can construct the entire world with it. And if you don't believe me, go check out Inigo's website or go check out some of the cool images on the Shader Toy website, and you'll see some of the really awesome stuff you could do with ray marching. And now here's a combination of an SDF, which is a combination of three smaller SDFs. So what it's doing is, okay, I've got my sphere distance, and it checks it with the sphere SDF. I've got my cube distance. I'm going to challenge this against the cube SDF, and then I'm going to do the intersection of my cube and my sphere. And that's really all that there is to it. All right, gang, not terribly complicated, really exciting stuff. I'm going to have to tell you guys to tune in next week if we're going to see some of this stuff in action. Really, really excellent stuff. All right, so check out Tech Art Talk live next week, and that'll be on the 9th of July, and we're going to have ray marching part 2. And remember, what we're going to be doing on is dealing with shading. And oh, golly, look at this. I totally forgot. Just to prove that this stuff works. Let me go back to where it is. Let me talk about where the thing. I forgot. I actually did have a proof of concept here. I totally forgot. Thank you very much for your patience, but check this out. All right, here we have something called Shader Tool. This is where I use to teach and do my development of HLSL. And so here we have, check this out. I have a quad going in as input. But what we're rendering is rendering out as entire sphere. You're saying, that's not a sphere, that looks like a circle. True. This looks like a circle, but what we have here is a non-shaded sphere. And so all we're testing is, okay, from the camera, is this sphere, are the points on here inside the sphere, outside the sphere, or on the surface? And that's all it returns. If it's inside of the sphere or on the surface, we're going to return red. And if it's outside of the sphere, we're going to return black. And so let's take a look at the code. Don't get too concerned about this HLSL stuff. This is really not that bad. All right, let me expand that a little bit. Okay, here's our assigned distance function. One's for a sphere. Here it is, the length of P minus 1. So we're just dealing with a unit sphere. And here's my overall Scene SDF. I'm just calling the SDF. And here we're going. The shortest distance to the surface, which is a term that I penned for my ray marching function. And this is the exact same ray marching function that I showed you folks beforehand. And then I have just this little function here that determines the ray direction depending on the camera location diving into the screen. You know, this is all about the ray stuff. This is where the rays come from, is this little function here. And so here is my pixel shader, which is doing nothing but, okay, I have my ray direction, I have the position of my eye, or the position of the camera, and then the shortest distance to the surface, and then very simple. If my distance is greater than the maximum distance minus the epsilon, then make it 0. So that's what is black. Otherwise, return red. And that's what we see. So this stuff does work. It's not real complicated. And this is what's really fun about this ray marching stuff. All right. So now let's terminate this lecture. Okay. Thank you very much for coming by. Check out on 7/9 what we're going to be talking about, ray marching part 2, and we're going to deal with Okay, how do you get shading on there if we didn't get any shading on it before? Okay, and then how do we move stuff? Because we're going to be modeling the world. We got to move this stuff. We got to translate it. We got to rotate it. And I'll show you how to do that. And we're going to show on how to implement this not only in HLSL but in something like UE4 as well. Okay, just as a reminder for everyone, if you happen to have an all-access pass to GDC this year, go ahead and check me out. It's 7/21. That's in a few weeks yet. But check me out at 1:20 Pacific Standard Time. That's in San Francisco. I'm going to be teaching my course on Object-Oriented Python Crash Course using Houdini. So that's right. You folks saw it here there first. Yeah, that's right. I'm going to be talking about the exact same course that I delivered onto my TechArt Talk Live about teaching Python really, really fast using Houdini. All right, if you like what you saw today, go ahead and subscribe to my YouTube channel. And otherwise, check me out. My name is Chris Rhoda. I'm on Facebook and on LinkedIn. Or you can check out Art EDU, which is the whole rigmarole, the whole conglomerate of everything that we're teaching here about technical artists. Check us out on Facebook and on LinkedIn. All right, if you want to help us out, go ahead to checkoutedu.com, which is the main website, and then go ahead and opt in. And what you do, if you give us your email address, then we'll send you out updates and things as they move and change, and so you will always be abreast of the newest developments going on here at TechArt EDU. All right, gang, I had a fun time today talking about ray marching. We're going to have even more fun next week when we go into how to shade ray marching objects and then how to translate them and then implement them inside of UE4. Really exciting stuff. Thank you very much for allowing me to share this with you. It's the 4th of July this weekend. Have a great weekend, and I will see you next week on another episode of TechArt Talk Live. Arrivederci.